Hey, this is going to be a walkthrough of the Rust book with terrible production value, really just more as a accountability exercise for myself. So, without further ado, I'm actually in the middle of reading this sentence, and so I'm just going to pick up from there. Curly brackets typically aren't used if the match arm code is short, as in listing 6.3 where each arm just returns a value. If you want to run multiple lines of code in a match arm, you can use curly brackets. For example, the following code would print lucky penny every time the method was called with a coin penny, but would still return the last value of the block 1. Let's see, here's my running code. I might should run this in here. Let me see what his command was. Cut that. Can I paste it in here? Nope. This is a mess. There we go. Okay, so let's make that match. And there we see that lucky penny is printed right there. Patterns that bind to values. Another useful feature of match arms is that they can bind to the parts of the values that match the pattern. This is how we can extract values out of enum variants. As an example, let's change one of our enum variants to hold data inside of it. From 1999 through 2008, the United States minted quarters with different designs for each of the 50 states on one side. No other coins got state designs, so only quarters can have this extra value. We can add this information to our enum by changing the quarter variant to include a US state value stored inside it, which we've done here in listing 6-4. Let's add that in code. Alabama, Alaska, Arkansas, California, Colorado, Connecticut, Delaware, Florida, Georgia, Hawaii, Idaho, Indiana. That's all I can remember. Okay. And then Let's imagine that a friend of ours is trying to collect all 50 state quarters. While we sort our loose change by coin type, we'll also call out the name of the state associated with each quarter, so if it's one our friend doesn't have, they can add it to their collection. In the match expression for this code, we add a variable called state to the pattern that matches values of the variant coin quarter. Where a coin quarter matches, the state variable will bind to the value of that quarter state. Then we can use state in the code for that arm, like so. This is similar to what I've done. Right, oops, right here. Yep. If we were to call value in cents, coin quarter, US state Alaska, coin would be coin quarter US state Alaska. When we compare that value with each of the match arms, none of them match until we reach coin quarter state. At that point, the binding for state will be the value US state Alaska. We can then use that binding in the printline expression, thus getting the inner state value out of the coin enum variant for quarter. Matching with option T. In the previous section, we wanted to get the inner T value out of the sum case when using option T. We can also handle option T using match as we did with the coin enum. Instead of comparing coins, we'll compare the variance of option T, but the way that the match expression works remains the same. Let's say we want to write a function that takes an option I32 and, if there's a value inside, adds 1 to that value. If there isn't a value inside, the function should return the none value and not attempt to perform any operations. So you'll have to take my word for it that I'm not reading ahead. And so what's the function called? +1. Sweet. If this is the most boring thing on YouTube, that's kind of the intent here. Let's examine the first execution of +1 in more detail. When we call +1 with 5, the variable x in the body of +1 will have the value sum5. We then compare that against the match arm. None gives none. The sum5 value doesn't match that pattern. Just realized I need to change this to sum41. So we continue to the next arm. Does sum 5 match sum I? Why, yes it does. We have the same variant. The I binds to the value contained in sum, so I takes the value 5. The code in the match arm is then executed, so we add 1 to the value of I and create a new sum value with our ch06 inside. Now let's consider the second call of +1 in listing 6.5, where x is none. We enter the match and compare to the first arm. It matches, there's no value to add to, so the program stops and returns the none value on the right side. Because the first arm matched, no other arms are compared. Combining match and enums is useful in many situations. You'll see this pattern a lot in Rust code. Match against an enum, bind a variable to the data inside, and then execute code based on it. It's a bit tricky at first, but once you get used to it, you'll wish you had this in all languages. It's consistently a user favorite. Matches are exhaustive. There's one other aspect of match we need to discuss. Consider this version of our +1 function that has a bug and won't compile. Well, it's missing the none branch. We didn't handle the none case, so this code will cause bug. Luckily, it's a bug Rust knows how to catch. If we try to compile this code, we'll get the error, pattern none, not caught, or something. Rust knows that we didn't cover every possible case and even knows which pattern we forgot. Matches in Rust are exhaustive. We must exhaust every last possibility in order for the code to be valid, especially in the case of option T when Rust prevents us from forgetting to explicitly handle the none case. It protects us from assuming that we have a value when we might have null, thus making the billion-dollar mistake discussed earlier impossible. Catch-all patterns and the underscore placeholder. Let's look at an example where we want to take special action for a few particular values, but for all other values take one default action. Imagine we're implementing a game where if you get a value of 3 on a dice roll, your player doesn't move, but instead gets a new fancy hat. If you roll a 7, your player loses a fancy hat. For all other values, your player moves that number of spaces on the game board. Here's a match that implements that logic with the result of the dice roll hard-coded rather than a random value, and all other logic represented by functions without bodies because actually implementing them is out of scope for this example. I've kind of committed to typing out all the code even if it's useless, so here we go. For the first two arms, the patterns are the literal values 3 and 7. For the last arm that covers every other possible value, the pattern is the variable we've chosen to name other. The code that runs for the other arm uses the variable by passing it to the movePlayer function. The code compiles even though we haven't listed all the possible values a U8 can have, because the last pattern will match all values not specifically listed. This catch-all pattern meets the requirements that match must be exhaustive. Note that we have to put the catch-all arm last because the patterns are evaluated in order. Rust will warn us if we add arms after a catch-all because those later arms would never match. Rust also has a pattern we can use when we don't want to use the value in the catch-all pattern, underscore, which is a special pattern that matches any value and does not bind to that value. This tells Rust we aren't going to use the value, so Rust won't warn us about an unused variable. Let's change the rules of the game to be that if you roll anything other than a 3 or 7, you must roll again. We don't need to use the value in that case, so we can change our code to use underscore instead of the variable named other. This example also meets the exhaustiveness requirement because we're explicitly ignoring all other values in the last arm. We haven't forgotten anything. If we change the rules of the game one more time so that nothing else happens on your turn if you roll anything other than a 3 or 7, we can express that by using the unit value, the empty tuple type we mentioned in the tuple type section, as the code that goes with the underscore arm. Here we're telling Rust explicitly that we aren't going to use any other value that doesn't match a pattern in an earlier arm, and we don't want to run any code in this case. There's more about patterns and matching that we'll cover in Chapter 18. For now, we're going to move on to the if-let syntax, which can be useful in situations where the match expression is a bit wordy.